We're here to share our work on developing laboratory assignments for NLP courses that teach students strategies of learning new ideas in NLP. We teach at two small liberal arts colleges, Harvey Mudd College and Swarthmore, which are undergraduate-serving institutions. Institutions like ours are usually small. The total undergraduate student body of Harvey Mudd is around 850 students, and Swarthmore is around 1,650 students. Small liberal arts colleges like ours tend to emphasize interdisciplinarity and impact on society. We try to avoid big lecture classes, and we aim to give our undergraduates curricular breadth by requiring a lot of coursework across the humanities, social sciences, and arts for all of our students regardless of major. At both of our schools, like a lot of places, computer science has become one of the most popular majors in recent years, which has increased the appetite among undergraduate students for elective courses like NLP. And if we're thinking about topics in computer science that have implications for interdisciplinary work and societal impact, NLP is an amazing option. However, since students have so many courses to take and our departments aren't huge, we have to keep our course prerequisites as minimal as possible. This leaves us with an interesting challenge. What do you focus on in an NLP course if you neither can have a lot of prerequisites nor a follow-up advanced version? In approaching this challenge, we decided to de-emphasize some of the host of models that one might implement in a typical Intro to NLP course. Instead, we try to focus on what skills and practices are necessary to study NLP as a broad area. Of course, this includes some standard topics in NLP, like regular expressions, n-gram language models, and so on, but it also includes things like how to dig up and visualize information about why a model is getting the result it gets, how to write code to process large text files and truly grapple with text data without getting stuck, and how to take those analyses beyond comparing which thing scores better to connect them to phenomena in the world. In service of these goals, we've taken a somewhat altered approach to the classic write code to implement this model and turn in the code, instead focusing primarily on student write-ups of their process as they implement and run small experiments. Our assignments leverage the idea of scaffolded discovery learning. For those of you unfamiliar with discovery learning, it's a pedagogical approach in which, instead of posing a concrete task like implement backoff for a smoothed n-gram model using these equations, instructors pose a problem, question, or direction of possible discovery for their students to work on, like, how do I compare how likely two sentences are? In this approach, students will discover the concepts, ideas, and tools they need to solve their problem, which can help them reinforce not only what the concepts are, but why they're useful. For instance, a student trying to address the question of probabilities for sentences might start with a model that uses frequencies from the original data, but doesn't have any smoothing, and quickly find it breaks whenever a new word or bigram arises. So they'll need some way to represent these things as having non-zero probability for their system to work. While this might take a bit longer than starting with the right approach to a problem, it gives students more clarity on why an approach might be useful. It also changes what students produce for their assignments. Instead of just grading based on the effectiveness of the solution provided, assessment can also include insights they share from their journey to the solution they found, including if there are places where a student demonstrated learning while their system wasn't working. Research on discovery learning has shown that it can be a great approach for learning with a few caveats. The biggest of them is that it's not enough to pose an interesting question and leave students to explore. It's important to provide instructor support and structures so students can eventually find their way towards success. In a class like ours, where we can't assume students are necessarily coming in with the same concepts to build upon, this scaffolding is extra crucial. We need to make sure students get ideas of what to try, refreshers on terms they'll need, and other types of instruction on their journey towards answering their question. To talk a little bit more about how we implemented our scaffolded discovery learning approach, I'm going to pass it off to Rich to give some detail about the 4 introductory labs we wrote.
The paper focuses on 4 labs that we did at the start of our courses. The first lab centered on a regular expression chatbot. In this lab, students took text input from the user and modified that input using regular expressions to produce a reply. The domain of the reply is open-ended. Students could build a chatbot similar to Eliza, or they could build a chatbot that repeats what they've said in Pig Latin, as shown here. In addition to teaching students about how to use regular expressions, students were encouraged to focus their time on analyzing their output rather than aiming for optimal performance. The second lab focused on tokenization and segmentation. The first part of the lab taught students how to do basic tokenization and counting, and asked them to think about issues of case, punctuation, and the impact of various normalization techniques on their results. In the second part of the lab, students built a sentence segmenter, which reinforced their regular expression skills from Lab 1. Lab 3, which is about word frequencies, types, and tokens, is the focus of the next slide, so we'll hold off in discussing that for now. In Lab 4, students were exposed to word embeddings. Students learned how to use NumPy to speed up computations and more efficiently store the large embedding dataset. In the second half of the lab, students learned how to use dimensionality reduction to visualize the embeddings of related words. They then displayed these relations in 2 dimensions, comparing canonical sets of related words to other related word sets that they constructed. In Lab 3, students are introduced to spaCy for the first time. In this lab, they only use spaCy for its tokenizer, and they reuse the Project Gutenberg text that they used in Lab 2. The goal of the first part of the lab is to see how well Zipf's law approximates empirical data taken from various texts. Students are asked to consider whether the author, genre, or length of the source text impacts their output graph. In plot A on the left here, a student has plotted the empirical relative frequencies of types in the entire Project Gutenberg corpus and compared it to the relative frequencies as predicted by Zipf's law. After testing on real texts, students used a variety of techniques to generate random texts and then repeated the experiment. In the center and on the right are 2 student-generated plots showing how well Zipf's law approximates randomly generated texts. In the second half of the lab, students learned how to extract unigrams, bigrams, and trigrams from news articles that had been labeled as either hyperpartisan or neutral. The datasets were too large for students to load into memory completely, so they learned how to iteratively process the data. Students were tasked with training an n-gram language model on each set of articles, and they investigated issues of data sparsity. Students were asked to think about whether the large number of unseen types in the test data gave them insight into the kinds of language used in hyperpartisan and neutral texts. Students were then asked to repeat the experiment, but this time by breaking the news articles into 2 random halves, containing both hyperpartisan and neutral texts. Above, a student-generated table shows the numbers of n-gram types and tokens found in one random half that were not found in the training data. Students were then asked to compare this result to the result they got when they trained on hyperpartisan news and tested on neutral news. A snippet of the text produced by a student is shown below. In this analysis, the student was surprised to see that the data sparsity issue persisted even when combining the news sources. One big takeaway from this lab is what conclusions we can and can't draw from distributional differences between 2 datasets. When they see that the results are similar, they experience a moment of panic because they feel certain that they must have miscalculated. With some reassurance that their calculations are correct, they move forward with a deeper understanding that distributional differences happen all the time, especially when you're dealing with sparse data like we encounter in NLP. They carry that lesson with them into the remainder of the course, which provides a healthy dose of skepticism in their reactions to future models they see. I'm going to pass it off to Julie to talk about keeping the discovery guided.
As students work through Lab 3, they're guided to discover a couple of crucial ideas in NLP. A lot of the guidance is designed to keep students on the right path. In other words, making sure that their code is working as intended, so that the time they spend writing about the implications of their code is focused in the right direction. As Rich described, one takeaway we want students to get is a real understanding of how to interpret frequency differences in language data, which we know always runs up against sparsity issues. In that case, a correct implementation of all the code for the assignment will lead to a result that is counterintuitive for many students. At least some students will wonder whether those counterintuitive results are really evidence of a bug in their implementation. Providing feedback along the way helps those students continue their work more confidently. In other cases, the goal of early feedback is to catch incorrect implementations before students use them to draw conclusions. An early concept that a lot of students struggle with is the difference between absolute and relative frequencies. When students plot empirical relative frequencies against theoretical absolute frequencies, they end up generating the graph on the left. We've built scaffolded checkpoints into lab write-ups with sample function input and output pairs that students can use to check the functionality of their code. But we've also built checks into the Gradescope autograder for each lab. In this case, we provide immediate feedback to students by showing the plot their code generates on the left, next to the plot our sample solution generates on the right when they submit their code. By guiding students to immediately see that there is a problem with their analysis, we're able to catch them before they engage in deep analysis of their output, in this case possibly leading to the conclusion that Zipf's law is completely inaccurate, and guide them to a correct plot before they begin the interpretive part of the lab. In addition to this visual feedback, we use autograders to automatically check for the correctness of individual functions. That lets us catch errors like this one, where a student extracted bigrams as strings instead of extracting tuples of words. By showing the student's output alongside the expected output, we provide enough information for the student to correct their own work. We think it's worth pointing out that our use of the autograder is maybe a little different than what people are used to thinking of as the role of an autograder. In our course, the autograder's job is to help students find and correct their own low-level bugs so that they know their assignment is able to be graded. The autograder is not the primarily grading mechanism for any of the labs. The total number of points allocated to autograder tests is trivial, but it helps us make sure that the write-up students submit are based on bug-free output. That way, we can more easily assess the quality of each student's write-up, which is where most of the points for each assignment come from. Since adding autograders, we found that the quality of student submissions has improved dramatically. Of course, providing feedback that lets students know their code is wrong is only helpful if they have the support they need to figure out how to correct it relatively efficiently. We've addressed that in part by having reserved lab work sessions with instructors available. We've found that we can quickly help students with some of the low-level things like file I/O that commonly trip people up, which lets them leave the lab time well prepared to engage in a thoughtful analysis for their lab write-up. More broadly, we fit this sequence of introductory labs into a variety of course structures. Some semesters we've used class time for traditional lectures. Other semesters we've had paper discussions with quite a bit of student autonomy in choosing reading topics from week to week. Beyond these introductory labs, some years we've continued with shared labs for the rest of the semester. Other years we've had students work on a common project, like a workshop shared task, with 1 or 2 labs dedicated to guiding them through building a baseline system, and then several weeks dedicated to improving their systems. In other offerings, students have completed more open-ended projects. We found that the skills developed in these first 4 labs are consistently valuable in supporting students in all of these different course structures. All of our Docker images, assignment write-ups, and starter code are available on GitHub. We're also happy to share our autograders with other instructors. Those aren't posted publicly since they include sample solutions, so please reach out to Xanda if you'd like to access them.